Hi. So for this week, for week 3, let me go to the roadmap, and then we are talking about the lab for week 3, and then we are talking about this particular lab A. So in this lab, what I want to show you is how the data was created. This part is not particularly relevant for this particular lab, but this is consider this as a review of the previous steps, and based on your first and second lab exercises, you are probably already familiar with most of its content, how to download the data from various sources and components, and then once you download all of this data, then merge all of this data. You can do it one by one, or you can do it together, and then you can check the target population to figure out that whether there was any issue. You can then try to get rid of some of the invalid values. Say for example, if some values were don't know or refused, you can get rid of them. And obviously you can check some summaries and recode some of the categories. If you have very specific categories in mind, then you can recode the variables, and then you can check some missing values and things like that to do your analysis. So I just want to mention that we have treated this data as a regular data. So far we have not done anything about the weight strata or clusters. So far we have not dealt this data as a survey data analysis data set. So we are just learning our ropes about basic regression in this particular lab. So we are not go into much detail about survey data analysis, which is a topic for week 4. Alright, so in this particular week, we are as simply assuming that this enhanced data that we have downloaded, this is a regular data. And that's why we are doing all sorts of subsetting and things like that that we are not supposed to do, but we are doing it here assuming that this is a normal data, just to use this as an example to show some of the regressions and diagnostics that we will do. Alright, that being out of the way, once you load the dataset, you will see there is a object called analytic, and this analytic is basically the data frame that we will be using in this particular lab. So if you simply use the str function, you can simply check what are the variables that are available in this particular dataset. You can see there is ID dataset, gender dataset already categorized. There are married, income. Income is a categorized variable already. You have diastolic blood pressure, systolic blood pressure, body weight, body height, BMI, waist measurement. All of these are numeric variable. You have smoke variable, and you have a bunch of other variables. So these all are numeric variables, and you have some other character variables. So to get a feel of the data, obviously str is a very nice way of getting an overview of the dataset, but if you want to get a bit more information about each of these variables in the dataset, you can run the describe function from the RMS package, and that will give you some interesting summary of the entire data. Say for example, for gender, it will tell you how many people are included in that variable, and then how many distinct variables or value levels are there. Say for example, in this we had male and female, so the distinct categories were there. Two of those were there. There were no missing values in the gender category. For age category, this age variable, if you remember, this age variable in here was a numeric value. So it is telling you how many distinct values are there, how many of them are missing, and things like that. Born whether in USA or elsewhere, it is giving you all sorts of description depending on what type of data. This describe function is very clever in identifying what type of data we are dealing with, and then tries to give a summary appropriate for that variable. Say for example, this diastolic blood pressure is a numeric variable, and it shows what are the lowest values and what are the highest values. On the other hand, when we were dealing with some categorical variable, it was giving us some sort of frequency and proportion. So depending on the type of variable, it is giving you different types of description. So you can simply try to get a quick overview of the dataset using this describe function. Obviously, one of the problems that you have learned in your previous courses as well, that if you have collinear variables in the dataset, that can cause some problem. And to roughly take a look at the data and try to get a sense of which of the variables might be collinear, you can use this var class function from this hmisc package to get a sense of which of these variables are being clustered together. So as you can see from here with this long line, and then you can see body weight, BMI, and waist variables. These are looking very close in terms of this clustering. So that gives you some sense that maybe this is something that we need to deal with later. Alright, so in terms of this correlation, there are other visual ways to try to identify which of the variables are problematic. Say for example, we can simply create a correlation matrix, and based on that correlation matrix, when we do the core plot, we can see some of these variables. Say for example, in here you can see body weight and waist variables are highly correlated. So you already know that there are some variables which are highly correlated, and when we try to identify some whether there was any correlation above 0.8 but below 1, you can see there are a number of variables that were associated with high amount of correlation. So far what we have done is we have tried to go through some visualistic plots to see whether there was any variables that were highly associated with each other. Let us go through some descriptive associations to try to figure out whether there was any high amount of correlation that was causing any trouble. Before doing that, let me show you some examples of how to get various summaries by category. Let me give you an example. So we know that cholesterol is a variable that was measured continuously, and since this is a continuous variable, we can simply take a mean of this. Say for example, you are interested about finding out what was this cholesterol level only for male and only for female. If that was the case, you can simply have the cholesterol levels for only male, and you can take a mean of it, and that will give you 190.7. Similarly, when you do the cholesterol level for only female, you can get a mean cholesterol level of 196.7. So this is one way, right? Remember, 190.7 and 196.7. You can use dplyr package to get the same. I'm not going to go into detail into how to do this piping and get the result, but I'm just showing that there are many different ways to get the same result. So this is the dplyr way, and that is giving you 197 and 191, and there is a dot, that means there is some other values there as well. Another way is to use the aggregate function. When you use the aggregate function and say that do the analysis by this gender variable, it gives you a detailed summary. You could use mean here to get just the mean, but summary does the same work, 196.7 and 190.7. You can use the describe by function from the psych package. Here, see what I'm doing here. I'm not really loading the package. I'm not requiring the package. I'm not loading the library. What I'm doing, I'm directly calling this function out of this package. So as long as I use this format of the package, I do not need to load the whole package. Sometimes what happens is that there are different packages that have same names, and if you try to load both of the packages at the same time, in one of the previous labs you have seen that then one package's functions get masked and other packages function becomes available. So if you want to avoid that, and if you are not frequently using the function from that package, you can simply use this double dot option to call a function without loading the package on your environment. Alright, when you do that, again you can get the mean for the male and female groups again, right? Again, you can do the tapply function when you specify the summary, and when you specify by which group you want to get the mean summary of this cholesterol variable, and you can see the mean you can extract from this tapply. So this is just to show you that when your objective is simply to find out what is the mean of one variable given some other factors in another variable, it is possible to do it in many different ways, right? But as you can understand, we have many different variables, and if you want to do this kind of process for all of those variables, that will take up a lot of time. Fortunately, there is this summary function, which is the base package function. You do not have to go to any other package. If you just mention which variable and by which other variables you need this summary, it will automatically give you the frequency. Say for example, for male and female, how many frequency was there and what was the mean of each of these groups, right? So for age group, whether born in US or not, race group, education, married or not, income, diastolic blood pressure, systolic blood pressure, by all of those categories, it will give you the mean. Notice that even though diastolic blood pressure and systolic blood pressure were continuous variables, right? But making a summary of continuous variable, so if you are trying to make a tabulation of two continuous variable, that will blow up. You will have huge number of values in the table. So to avoid that, this summary function is very clever in identifying that since both of these are continuous variables, let's not do a continuous variable to continuous variable table, and it automatically categorizes the diastolic blood pressure, and it gives you some mean within each of these levels, right? So say look at these values. Say diastolic blood pressure 0. So I'm not a doctor obviously, and I do not know whether this is possible or not, but based on my limited understanding, see, this systolic blood pressure is starting from 80 and this diastolic blood pressure is starting from 0. This is looking suspicious. So let me take a look at the data to figure out like what is going on. So in here what I'm doing is that I'm just trying to get a summary of the diastolic blood pressure, and then when I see 0 is the minimum value, but after that it gets 62, 70 and 78, 112 and things like that. So this 0 value I do not trust. I'm assuming that this is some sort of mistake, so I'm simply assigning a missing value in that 0 value, right? All right. So other than numeric summaries, we can obviously do this kind of plotting. And in this plotting, I don't know whether you can see this triglyceride function has very low value versus very high value for the cholesterol, but all of the other variables are giving sort of the same type of mean values for cholesterol. So this is something is going strange for the triglyceride variable. And when we try to do a Spearman 2 correlation, we can see this triglyceride variable is actually highly associated with our cholesterol variable, right? All right, so probably it can happen that this triglyceride variable is highly predictive of this cholesterol. So maybe this is enough to make our modeling work, right? So let us do this simple linear regression, right? So for that simple linear regression, the formula is cholesterol is our outcome variable and triglycerides is my independent variable or the predictor of cholesterol, right? I save that as a formula and I simply use that formula in my linear model and I fit the summary of it, and I can see these are the summaries and these are the coefficients and these are the confidence intervals, right? And I can also plot the residual plots and all of the diagnostic plots that are available within R by default. One thing to note is that even though R or any other software will immediately print out a lot of these diagnostic plots, unless you are explaining them in your manuscript, it is probably not a good idea to paste them in your manuscript. So because there are many different diagnostic plots checking many different assumptions and maybe not all of them are relevant to you, so it is probably good idea to have only the relevant ones in your manuscript or in your report writing. All right, so obviously when you are seeing a residual plot and you are seeing a red line like this which is deviating from your dotted line, there is something wrong going on, but let us investigate it a bit further. So when I plot cholesterol and triglyceride, so cholesterol is in this side and triglyceride is in this side. So see, all of the points are here. So how many data points do we have? In general, we have about more than 1000 subjects, in total 1267 subjects, right? And then out of them, most of them are in here, but 2 points are in there when we are plotting this triglyceride and cholesterol. So these 2 points are probably going to be highly influential, right? So if you want to figure out which subjects or which person is associated with these 2 different points, what you can do is that in the analytic data you can simply subset for triglyceride greater than this value, right? And that gives you the ID of this and this in the data set, and you can figure out like what is it that is going on with these 2 persons. So these 2 persons are male and they are mid-aged, and you can try to figure out many different combinations to try to figure out why these 2 persons are associated with this triglyceride that are very high, right? And if you think that this is bringing down your model and compromising your model, maybe you need to do something about it. All right, so there is something called leverage plot, and you can try to again plot the leverage with respect to your student residual plot, and you can see there are a couple of plots that are looking very suspicious. So I think these are the row numbers associated with the data. and you can again plot those, and you can see the leverage plots in terms of the index. There are a couple of points, especially this point is much higher. So you can try to figure out like which of these points are above 0.05, and you can see how many. There are one person who is above that point. So everyone's leverage point is here, but one person's leverage point is here. Maybe you need to figure out whether that person has some unusual covariate characteristics and whether you want to keep that person in your study. So you want to try to figure out whether there was anyone below certain value, above certain value. You can try with this, but that doesn't seem to be a problem in terms of this particular residual plot. Alright, so we have already figured out that there were two persons who were above 1500, and if you think that those are problematic subjects, you should not try to consider them in your study. Particularly, see, if you go up, you will see, so what are the IDs? 88018888576, and according to the leverage criteria, you can again see 88018. So this is the subject who is repeatedly causing trouble in many of these diagnostic criteria. So obviously you have to make a judgment call of whether you want to keep them in your study, or you think that these are extreme values and that are distorting your relationship of interest. You have to make that judgment call. So in this particular study, since these triglyceride values that we have seen earlier are looking very different compared to rest of them, I particularly made this call of not including these two data points that are probably dragging my analysis or association results. But obviously this is a controversial topic to delete your observations, and you need to think very carefully about whether you want to do that or not. So in this particular study, I have deleted two subjects out of these more than 1200 subjects, and I want to refit my clean data. So my new data is which one? This analytic 3, and I just want to fit the same formula, the formula 0 that I have defined earlier. So our formula 0 was simply modeling cholesterol with the triglyceride, and in terms of that, when we fitted the new model, we use this published package to see the output, and these are the coefficients and these are the confidence intervals. So I generally prefer to use published package because the output of published package is much nicer compared to any other summaries. There are many other tools that gives you similar type of output. Say for example, there is a package called JTools, and there is a function called sum within that JTools package that gives you very similar output like this. It's a matter of personal preference, I guess, that I use published package here. Alright, so remember the residual plots we were talking about. We again feed those residual plots here. See this, there is a deviation. This red line is somewhat deviated from the ideal dotted line here. So there is a function called CR plot, which is basically the component plus residual plot, often known as the partial residual plot. So you can see for the triglyceride, this partial residual plot is giving you this blue dotted lines, but this pink line is deviating from here. So as we know, so this pink line, you can see this line looks like there is a curvature going on, right? And whenever there is a curvature going on, it is a very good idea to use a polynomial term to see whether we can get rid of this type of curvature. So based on that suggestion, what I'm doing here is that I'm using a polynomial of order 2. I can define it either in this way or in this way. Incidentally, the published package cannot recognize a polynomial order if we define it in this way, but it can recognize it if I define it in this way. That's why I'm using the second one here. So when I'm writing in the same object twice, R will always take the second one, and I'm using the formula 1 to fit the linear model, and I get the coefficient and the confidence interval, right? And the CR plot now looks like this. So I can still see there are some curvature that is going on. So I increase my polynomial order. When I increase my polynomial order to order 3, I can still see this is this curvature is still there, right? So so this is obviously a bigger plot and this is a smaller plot. It is hard to see from this plot whether this is actually changing anything. But based on the visual inspection, it does not look like it is changing a lot in terms of improving the model fit in terms of this diagnostics component plus residual plot. All right, so obviously we have tried to use the triglycerides as the one independent variable to fit our model, but obviously there are many other variables in the same dataset, and we want to see whether the other variables have anything to contribute in the model. So we include many different variables from the enhanced dataset, and we fit it using this formula 3, and these are the results that we are seeing. One of the things you should probably try to check whether the confidence intervals are somewhat unusual in some cases or not. So if you are seeing something like a confidence interval from 0 to 1000, that should concern you, depending on the data of course, but generally speaking, if you are looking at a very wide confidence interval, that should concern you, because remember in the previous collinear predictor we have seen there were some variables that were somewhat associated, and also when we did some of the descriptive associations, we have also seen that the triglyceride variable was highly associated. But in terms of the diagnostics, we simply want to see from the linear regression whether we can identify any problem due to those collinearity that we have seen earlier. So in terms of this regression coefficients, nothing seems out of ordinary, although there are some high values, but maybe those are not too high to be concerned about. So when we fit the collinearity measurement or VIF from the car package, we see some of the variables are associated with high VIF, and interestingly enough, you see the BMI, body weight, body height, waist, some of the variables that were clustered together previously when we have done this identifying collinear predictors, those variables are being flagged as problematic variable in terms of this generalized VIF. There are many other ways to obtain the VIF values in R, and we have used them, and we can see that those 4 variables are again identified as problematic variable. So whatever variables that are more than 4 are generally recommended to be investigated further, and we can see these are the variables that are the culprit here. Alright, but I think one of the things we should note that even though we have collinearity is a data issue. It's not necessarily a big problem unless it is destroying your confidence interval in such a way that the confidence interval blows up, right? So nothing like that happened, but just to be cautious, you can also try to fit another regression by excluding these variables. So in the code, when I'm putting this comment here, that means whatever is on the right hand side of the hash sign, this is not being read by R. So R is only taking BMI from this line, and then it is directly going to triglyceride and uric acid and things like that. Alright, so and you can see that, say for example, what is the BMI variable? After this BMI, I have triglyceride. I do not have either any of these variables in my regression fit now. And when I do the VIF calculation and try to check whether any of my VIF is greater than 4, it says nothing is greater than 4. Again, I want to stress that if VIF is not causing any problem or causing any instability in your analysis, maybe it's not too much of a problem, but when you see a VIF like 101, maybe you should investigate further and try to see whether that is impacting your analysis in any way. Alright, so far we have dealt with a continuous variable. Let's try to make it a binary variable. Say for example, cholesterol less than 200 is obviously something that is not unhealthy, so we are going to define this as healthy and unhealthy depending on this cut point 200. Less than 200 means healthy, greater than or equal to 200 would mean healthy, right? So according to that criteria, we have this categorization and frequencies, and then we try to fix unhealthy as the reference, because by default what R tries to do is it tries to put whatever is lower in terms of the alphabetic order, it will try to put that as a reference category. But maybe you want unhealthy to be in the reference category and healthy to be something that you want to use in here in your regression. So you can set your reference category using the relabel, and then you can use the whole list of covariates, including the covariates that were problematic, right? And you can try to fit your logistic regression model when you say your family is binomial, and you can again try to inspect whether there is any odds ratio that is blowing up. I do not see any, and whether there is any confidence interval that is blowing up. As far as I can see here, it doesn't look like any confidence interval is associated with very high confidence interval width. Alright, but again, when we try to assess the VIF, that's why this generalized VIF is used, because generalized VIF can also calculate the VIF for the non-continuous outcomes or binary outcomes. So here again you can see the same level of problems in the BMI to waist variables, so probably we want to keep only one, but that part we will do a bit later. In here what I'm trying to do is I'm trying to calculate the AUC values. So I'm using this PROC package to get the AUC values, and from that object I'm getting the AUC value of 0.74. When I'm remodeling with deleting all of the variables that are were highly associated with BMI, I again calculate the odds ratios and confidence interval. None of these confidence intervals seem to change too much. And then when I calculate the VIF, nothing is greater than 4, and when I calculate the AUC, you can see the AUC is very close. Now it is 0.7406. Previously it was what, 0.7411. So there is slight change in the third significant digit, but in terms of your model fitting, the collinearity was probably not impacting too much. So you can try to decide whether you want to keep those variables or not, but generally speaking, you probably need to think a bit more about, say for example, when you are including all of these variables in your model, are they really giving you very similar type of information? Say for example, when you are putting BMI in your model and then you are putting body weight in your model, is it really changing in anything in your model other than predictive ability? So if your goal is to have high predictive ability, that could be one reason to put this. But if you are trying to do a causal modeling and you are trying to put all of these variables that are associated with a similar concept, all of these are associated with some sort of body weight or highly correlated with body weight. So you need to think about whether in a causal type of model you would include those type of similar concept variables in your model. Even in a predictive model, when you include highly collinear variables, that is often a problem, and later in this course we will learn about shrinkage method that can deal with this kind of problem in the predictive modeling sense. So once you have changed your dataset to some extent compared to the original data that you have loaded, because you have deleted some patients, so you should probably save this image, and this dataset is something that we will use in our next part of the lab.